Hey everyone. So in today's video, we're going to be using a GLM approach to be doing what we would normally think of as an ANOVA. And that's basically just a categorical predictor for a numeric outcome. You can think of it in terms of, how does the group I'm in have an effect on whatever outcome that it is I'm measuring. And we're using a general linear model approach, or GLM approach, because from the last few videos and the next couple of videos, you'll see that we can use this strategy for almost any type of analysis that we want to do. And today we're going to use it on a categorical predictor with more than 2 categories. So there might be 3 groups or 4 groups or 5 groups. So let's get right into it and I'll show you an example of how we do that. So let's go into my R screen. Here we are in R, and in fact, because I'm going to be showing some plots in the panel that's right behind me, I'm going to put myself up into the upper corner and make it a little bit easier for us to see everything. Okay, I'm going to start off by opening up a new script file. So let's just do a new R script. And I usually like to start off by using the options SciPen equals 999. And what this does when I run that, I used Control Enter to do that. What this does is it makes sure that R doesn't put its output in scientific notation. I just find it a lot easier to read that way. If you want scientific notation, you don't have to bother with that, or you can use SciPen equals 0. Then we're going to load up our FlexPlot library. So FlexPlot we're going to use for a few different functions for this, mostly for visualizing our data, but also a couple more functions that are built into FlexPlot. So I'm going to use library FlexPlot in order to load up the FlexPlot package. Now, if you don't have FlexPlot installed, you can't do it through the normal method. Go back to my visualizations video and I talk you through how to install FlexPlot and then load it with the library function. Okay, so the first thing we're going to do is actually use a data set that's included in the FlexPlot package that's called exercise_data. And what I can do, because I've got the FlexPlot library loaded, we can just view by using the view command, exercise_data. And unfortunately, I spelled that wrong. So it's exercise data. There we go. What we see is this basically gives us some different outcomes in terms of we've got weight loss, we've got gender, we've got rewards, income, all kinds of different things as a function of this therapy type. So there's control, there's a behavioral, BEH, or cog, so cognitive therapy. So it was just different types of therapy on these different outcomes. So we're going to have a look at that because it's a categorical variable that we can use. And we can see that there's 3 groups: the control, the behaviorist, and the cognitive group. All right. So what we're going to do is, now because I clearly spelled exercise data wrong once, I'm actually going to copy this data set into something I'm going to call D, and D for data. And that just basically makes it so I make a few fewer spelling mistakes. And we can see here now I've got my data set over here as an option right behind me. It is named D, and it's a data frame with 200 observations. Okay, so that's the data set that we're going to be working with. And we can actually plot the different types of variables that we're going to use. So we're going to be looking at weight loss as a function of the therapy type. So that's what we're going to be doing. So if we use the FlexPlot function, and we're going to look at weight.loss as a function of 1, data equals D. And what this is going to do is this is going to plot a histogram of the weight loss. And we just want to see if there's any problems like, some value that doesn't make sense. But in the figure below us, we see it's reasonably normally distributed. Some people gained 10 pounds. That's what minus 10 pounds in weight loss would be. And some people lost up to about 20 pounds. So that looks all reasonable to me. We're also going to do the same command. I'm going to copy and paste that, but instead of weight loss, it's going to be therapy.type. And because this is a categorical variable, it'll just give us the number of observations, or in this case, subjects, in each of those groups. So if I run that, we see, okay, we don't have too bad of an imbalance between the numbers in each group. Looks like there's almost 80 in the behavioral group and about 60 in each of the cognitive and the control groups. So they look reasonably good as well. The last thing I'm going to do is I'm going to plot weight loss as a function of therapy type. And I'll just get rid of this as a function of 1. And run this command. And this is the analysis that we're going to be actually looking at. So we see in the graph below us, we've got our 3 groups: cognitive, behavioral, and control. And so we're kind of interested to see is there a difference between these groups? So the first thing we can do is create a model of that. And I'll use the linear model command, and I'll create an object called M. And into M, I'm going to put, well, basically this whole command here. So I'm going to go LM, and I'm just going to paste what I had there. Weight loss is a function of therapy type, data equals D. So this will just do a linear model of that thing that we've actually got plotted right below us here. So I create a model, and we can see that it's now appeared in the environment right behind me. The first thing we may want to do is have a look at the diagnostics before we go any farther, just to see that there's no massive problems with our data. And the way we can do this is we can use the visualize function, which is built into FlexPlot. Visualize M. And this will give me the model. Of course, I don't like to spell things quite correctly, so visualize, much better. Try that one more time. Okay, so what we can see in the plot below me here is it's given us our figure of the model now, which is looking fine. A histogram of the residuals. Remember, we're looking for reasonably symmetrical and nothing too far outlier. We've got a few outliers at the bottom end, but I don't think it's anything we have to worry about. And our spread location plot, it looks like we've got a reasonably flat line. It looks like essentially our distribution of our residuals is basically the same across all the 3 different groups, or the 3 basically means. So this all looks reasonably good. So now that we've got that, we can look at a summary of the model. So if I go summary of M, what this will do is it gives me a bunch of different information. What we see is the coefficients I get an intercept, which, remember, when it's categorical variables, that is one of the categories. And we can tell which one it is because it's neither of these two. It's not cog and it's not BEH or behavioral, so it must be the control group. So the control group is considered the intercept. And if we look at the figure over here, we can see the control group's value is somewhere around 5 or just under. And we can see that, oh no, in fact, it's 4.13. Okay, great. Now, what it's telling us is that is different than 0. And we don't actually care. That's not really that important for what we're looking at here. And then our estimates here are telling us the slope, or the mean difference, for the cognitive group as compared to control. And so they are 3.506 larger. And the behavioral group as compared to control are 3.44. And those are both showing as significant. But the thing is here, in this analysis, we want to really look at whether there's an overall effect of the the three groups. And the other thing is that it's not giving us all the different comparisons. Now, what it does show us in the very bottom here, we can see I've highlighted it, that we basically have an F statistic or an F ratio here of 8.5 on 2 in 197 degrees of freedom and a p-value of 0.000286. Now, this tells us something about the overall analysis. Another way we can get at that is by using the ANOVA command. And the ANOVA command basically is the same idea as running an ANOVA test. So the ANOVA is useful in this case for giving us basically our output table that gives us our mean square and mean square errors and our degrees of freedom and calculates our F ratio. And this will give us the whole table. So if I type ANOVA of M and run that, we see that we get an overall value here. So we have our sum of squares and our mean square on our degrees of freedom, our F ratio, which is 8.501, and we can see that's the same thing that it showed us above. And our p-value of the entire analysis is 0.00028, and that's the same thing it showed us up here. So that allows us to see that overall effect. So one more thing we may want to do is use another function that's built into the FlexPlot package called estimates. And estimates of M will show us basically a few different extra things. So we've got a full model R squared. So this will tell us that looks like the model accounts for about 8% or 7.9% of the variance. And it gives us our estimates for the different means. So we have our control mean, which was 4.13 we saw before, and then the mean for the cognitive group, which is 7.64, and the mean for the behavioral group, which is 7.57, as well as the differences, upper and lower confidence intervals, as well as Cohen's d, or effect sizes for each of those different comparisons. So we can see the effect size for cognitive versus controls, 0.64, behavioral versus controls, 0.63, and behavioral versus cognitive is a very small effect size of negative 0.01. But we don't have p-values for these here. So one way we can get at those, and we can actually get around some of the problems of multiple comparisons, is by using the emmeans package or emmeans function. So you may need to either install emmeans if you don't already have it, and if you do already have it, you're going to need to load that library. So we're going to use the library function, library emmeans, so emmeans, and we load that. It says welcome to emmeans. That sounds good, no problem. And then we can use the emmeans function to give us some of this same information. So if I just type emmeans, so emmeans, if I just typed emmeans m, it's going to give me an error because it needs some parameters. It needs to know what we need it to tell us. So I'm going to go comma. If we give it emmeans as a function of therapy.type, what we can see is the output that it's given me is very similar to what we have for estimates. There's upper and lower confidence intervals, as well as the actual means and standard error, degrees of freedom, things like that. So that's okay, but where it becomes a lot more useful is if we use the same command, but we tell it we want pairwise differences. So the way we do that is we tell it pairwise as a function of therapy type. So now when I run that command, what we see is we still get the same thing out. We get the estimated marginal means. It's the same tables we have above, but we get an extra table with these contrasts. And it shows us the difference. So negative 3.5, the standard error difference, t-ratio between those, as well as p-values. And note that these p-values now have been corrected using the Tukey method for comparing a family of 3 estimates. And what this is doing is it's doing post hoc pairwise tests, but it's doing a correction to make sure that we're not inflating our probability of a type 1 error by just doing multiple t-tests. It corrects the p-value. So by default, emmeans will use a Tukey method for doing the corrections. Now, another way you could get this output is by using this first command that I put here, so not using the pairwise, and putting it into some object. So I'll just call it emm. And if I did that, and I create a new object of my estimated marginal means, then I can use the pairs command on emm. And what we see is when I run that, it actually will not give me the estimated marginal means, but it will just give me the comparison between the pairs, which is the same thing that we see down here. Now, again, by default, estimated marginal means, emmeans, uses the Tukey method for correcting for multiple comparisons. But you can use different methods. You could use a Bonferroni method. You could use a Holm-Bonferroni. You could use a Benjamini-Hochberg, or you could use no correction, which actually isn't really probably a good thing to do. But what we'll do is I'll show you what these things do and what kind of different output they would provide you with. So if we did this and we said emmeans of m pairwise as a function of therapy type, and then we put adjust equals, quote, none. So this would be no adjustment. What we see is the p-values that we get out now are actually quite a bit smaller in comparison, right? So for cognitive versus control, our p-value was 0.0015. But without an adjustment, it's 0.0005. So we can see that these are actually a little bit lower probability or more significant. That doesn't actually make sense. Now, what the Bonferroni method is, which is the one that probably most people are familiar with, is it basically takes your p-value, the uncorrected p-value, and multiplies it by the number of comparisons that you've done. And in this case, it's 3. So if we, instead of using none, we used Bonferroni, so Bonferroni, we can see now that what it does is it takes those values and multiplies them by 3, right? So we've got 0.05, that's 0.15, 0.03, that's 0.09, 0.9402 would be 2.7 something, but obviously probability can go only between 0 and 1, and therefore it rounds it up to 1. So you can use Bonferroni, you could use Benjamini-Hochberg, which is basically called the false discovery rate. That's another really good one to use. It's just BH. Or you could use Holm-Bonferroni, SIDAC, a few different other types of corrections. All right, so hopefully that's given you a good idea how we use the general linear model GLM method to do an analysis of variance, or basically the comparison of a single variable that's a categorical variable with multiple levels on a numeric outcome. And then also how you can do the post hoc multiple comparisons on those and make the appropriate corrections. All right, look for me in my next videos.